This is 16.7, number 3, another center of mass question. So we want to find the center of mass of this surface, and this is a cone between 1 and 4 for height. Because it's a cone and it's based on a circle, I'm going to parameterize it as a circle. So here's the parametric. R is going to be an R of UV, but we could have just as easily used R theta. I just hate to use R for the function and for the radius, so that's why I changed it to UV. So V is going to represent the radius. It'll be V cosine of U and V sine of U. So with U being 0 to 2 pi and V gradually increasing as we move upward, this will make circles of greater and greater radius as we move up in a V direction, and this will draw out this cone. You'll notice that Z is just equal to the radius, which is equal to V, which is equal to the radius. So it all makes sense. And then because V is equal to Z, that makes our V go from 1 to 4. So that's its parameter. And then U is going to go from 0 to 2 pi. And this will draw out the whole cone in exactly the way we want. All we got to do is rewrite our sigma. So sigma is x squared z. X squared is v squared cosine u. And then there's an extra z, which is an extra v, so it's just v cubed. So there's our sigma, and then we got to work out what our argument's going to be. So r of u is equal to negative v sine of u, v cosine of u, and 0. And then r of v is going to be cosine u, sine u, and 1. And now for our cross product, ru cross rv. The cross product is going to be, the ith component is going to be v cosine u. The j component is going to be v sine u. And the kth component is going to be negative v sine squared, negative v cosine squared, so that's just negative v. And then we're going to find the magnitude of this, so ru crossed with rv, magnitude, and that's going to be, of course, v squared times cosine squared plus sine squared, which is 1, plus another v squared, so it's 2v squared, and that's all under the radical, so it's radical 2v. So there it is. There's our argument. There's our sigma. So our m integral is going to be the integral from 0 to 2 pi in u, and 1 to 4 in v, and the argument's going to be radical 2 v to the 4th cosine squared u dv du. And this turns out to be pretty messy by the time we're all done. This gives me radical 2 times pi times 4 to the 5th minus 1, and we'll eventually work that out, over 5. And then once again, this guy, because it's an upward opening cone, is symmetric in x and y, so I only need m x, y. I just need the z part of the moment. It's going to be the same integral, 0 to 2 pi, 1 to 4, and then the whole argument is the same. The only difference is I have to add in a z, and of course an extra z means an extra v. So it's just radical 2 v to the 5th cosine squared u dv du, and unsurprisingly it works out to be radical 2 pi times 4 to the 6th minus 1 over 6. And then we need the ratio of these guys. Again, m x z equals m y z equals 0. So the center of mass is 0, 0, and the z component is a humdinger. It's 5 times 4 to the 6th minus 1 over 6 times 4 to the 5th minus 1. So it's a number that's significantly, no, it's not less than 1. It's got to be between 1 and 4 because that's where the z parameters are. I think this turned out to be approximately 3.34. So it was pretty close to the top end, which you would expect with a cone. Most of its mass is at the top. So there it is, another center of mass question utilizing this new way of doing surface integrals.